Okay, so we're starting. Hello everyone, and welcome to the Electrochemical Colloquium. Today we're discussing scanning probe microscopy and how it can be used to study solid-liquid interfaces. As you know, electrochemical reactions at such interfaces strongly depend on the structure and dynamics of the double layer. And so it can be quite challenging to probe such interfaces in situ. One way to probe solid-liquid interfaces is by the surface X-ray scattering, and this is what we discussed previously with Yvonne Grunder in the colloquium number 2, and that was more than a year ago. So if you're curious, you can go ahead and take a look at what kind of discussion we had. And there's another way, which is to use scanning probe microscopy and try to get atomic scale insight into the properties of interfaces. However, such atomic scale experiments can be very challenging, especially when it comes to data interpretation. So this is what we're going to discuss today. Our today's speaker is Professor Ricardo Garcia, who is a leading expert in atomic force microscopy of both organic and inorganic and biological materials, and he is the inventor of a number of force microscopy techniques. Over several decades, he has made very important contribution to imaging of solid-liquid interfaces, to nanomechanics of soft matter and biophysics. Ricardo received his PhD from the Autonomous University of Madrid and did his postdoc at the University of New Mexico and the University of Oregon. In 1994, he became a scientist and then in 2004 a professor at the Spanish National Research Council. Ricardo, thank you so much for joining us today, and we're really happy to host you here. Now the stage is yours.
Thank you, Andrew, first for the introduction, the kind words, and also for the invitation to the Electrochemical Online Colloquium. I am very happy, and it's an honor to deliver a talk. And as you have mentioned, the AFM has a lot of things to say on solid-liquid interfaces and electrochemical properties of solid-liquid interfaces, but as you mentioned, it's a challenging topic with many things to be clarified and to be understood yet with respect to the technique. So let me share, let me share my screen. Okay, so this is the title, yes, AFM on solid-liquid interfaces, and I will try to give you an introduction and an overview of the fields from the more basic concepts to the more advanced concepts. So let me just say that of the three environments where the AFM can operate, ultra-high vacuum, air, or liquids, liquids represents the most challenging and the more difficult environment, both from the conceptual point of view, because the theory of the AFM imaging in liquids is more complex than in air and ultra-high vacuum, and from the operator's point of view, the handling of an AFM operation and interpretation of the results at the highest resolution in liquid is also more demanding than in air or in ultra-high vacuum. So for that, those reasons, in a sense, the AFM applications in liquid are still under development. So, so I will give an introduction to generally to the AFM, and then I will introduce the basics of the theory of AFM in liquid. And after that, we will go through applications and the latest advances in high-speed AFM and three-dimensional AFM. Well, let me say that the AFM was invented 36 years ago by Gerwinnik. Gerwinnik, Calvin Quaid, and Christopher Gerber. And actually about 14 years ago, a major journal in material sciences, Materials Today, made a ranking of the top 10 advances in material science since the Second World War. And they came up with the idea that the scanning probe microscopy, in particular the AFM, ranked second, just behind the international roadmap of semiconductors or the microchip development. So that tell us the impact that in these 36 years the AFM has had in the material science community. Well, for that reason, among other things, Gervini, Christopher Gerber, and Calvin Quaid got the Kavli Prize in Nanoscience in 2016. Well, let me see in a single slide why this has happened, or why the AFM has had such an impact in science. Well, the first thing is because just restricting ourselves to solid liquid interfaces, the AFM is the only microscope that can give you atomic resolution images of surfaces in liquid. You can see the ions, you can see the water molecules. You can also obtain with sub-nanometer spatial resolution the imaging in buffer solution of proteins, imaging dynamic processes of interaction of biomolecules, imaging mechanical properties of cells, polymers, and the AFM has also generated force spectroscopy measurements with capability to imagine single molecular bonds, and some applications on scanning probe lithography, because all of those things put all together explains the impact that the AFM has had in material science and molecular and cell biology in particular. Well, let's go back to the year that the AFM was invented. At that time, there were two major microscope techniques: optical microscopes and electron microscopes. And actually, you think about it, those techniques, though they use different particles, photons, or electrons, they share a common principle in the sense that you have an incoming beam that you send to the sample, and then you analyze the reflected, scattered, or transmitted beam. Binik, Gerber, and Quaid proposed a different approach, and the approach was just not to use either waves or particles to image a surface, but just to introduce the concept of mechanical forces as a means to get high spatial resolution images. And that was, at that time, a radical concept. And this is the AFM, so the concept of having a molecular finger that enables you to read, to see the position of the atoms or molecules on a surface. So we get to the conclusion, or to this idea that the AFM is a mechanical microscope, a microscope that operates sensing, measuring, detecting mechanical forces. Which type of forces? Well, the forces are of electromagnetic origin, certainly, but they could have different time dependencies, distance dependencies. So we could have long-range van der Waals forces. We could have hydrodynamic forces. We could have short-range repulsive forces. Also, we could have some short-range forces called adhesion forces. And we could have magnetic forces, electrostatic forces. So this is, for the AFM, is both a source of potential possibilities, but also a problem, because at the end, the sensor senses forces. So no matter which the force is applied at the end of the tip, you are going to be sensed. So at the end, or to be prof. So at the end, you need to develop certain protocols to separate the different interactions, which could be challenging at some time. About how the AFM operates. So the concept developed by Binik, Quaid, and Gerber was just the molecular finger concept, that you have a molecular finger that is in mechanical contact, so with the sample surface continuously. And this was good to start the instrument, but it's not good because at the end, people realized that it was difficult to control the strength of the force that you apply in what they are called contact or quasi-static AFM modes. So for that reason, to overcome the problems associated to applying excessive forces on your sample, the dynamic AFM modes were invented. And these modes, where you have an oscillating cantilever interacting with the sample, enable you two things. You gain two things by operating in dynamic AFM with respect to a quasi-static AFM. You gain more parameters to measure properties of your sample, because the oscillation has amplitudes, has phase shifts, has frequency shifts, and those parameters reflect the interaction in a different way. And the other thing that was gained by using dynamic modes was that one can control the force that apply on the surface better. And actually, there are two main dynamic AFM modes. One is called amplitude modulation AFM, where the parameter that you use to the feedback for the operation of the instrument is the amplitude of the oscillation. And the other mode is called frequency modulation AFM, where the parameter that you use to track the properties, topographic properties of the sample, is the frequency shift due to the interactions. So let's see how the interaction in a dynamic mode is modified by the properties of the sample. So usually what you have is this oscillating cantilever that when it's not interacting, it has a resonance like this. And when you interact with the sample, if the interaction is repulsive, what is going to happen is that you are going to shift the resonance curve to the right, to higher frequencies. However, if the interaction with the sample is attractive, then the shift goes to the other direction, to lower resonance frequencies. So this is the way the interaction works in the modifies the resonance frequency of the instrument. Of course, not always the interactions are elastic. Well, actually, most of the times have some inelastic component. And what happens is that you get both a shift in the resonance of your vibrating cantilever and a decrease of the amplitude of the oscillation because there is some dissipation. So now let's go. I think it's very important to understand how the AFM operates in liquid and how the AFM can increase our capability to image at atomic scale resolution solid liquid interfaces and electrochemical environments is relevant really to understand the equation of motion of the AFM in liquid. So let's start with the general equation of motion of this vibrating cantilever schematized in one dimension. So we have the cantilever with the tip that oscillates up and down. Which is the equation of motion? Well, the equation of motion, as a first approximation, we will consider the Newton equation. And then we can put in one side the forces, in the other side the other elements. So let's describe. First, what we have here is the tip sample force. Actually, this is what we are interested in AFM. In AFM, what you are interested is in identifying in the tip sample force, because that carries the information on the properties, topographic, mechanical, magnetical, electronic of your sample. The second term that we have is the driving force. For the cantilever and the tip to be able to oscillate and to keep the oscillation continuously in a medium, we need to apply a force continuously. This force is a sinusoidal force. On the other side of the equation, we have the inertial term. We have the tip that has some acceleration. We have another term here, and this other term reflects the fact that the cantilever and the tip, when they move, displace the molecules of the environment, in particularly in liquid, the liquid molecules. This is enclosed by this term that depends proportional to the velocity. And the last term is just the cantilever deflection, because to a certain extent, the cantilever works as a spring. Now, which is the solution of this equation? The solution of this equation is this one, where we have a static deflection. There is always a DC component. Then we have another component that is a transient term that we are going to have always for a system that is driven and in an environment with damping. And this transient term vanishes. And actually the characteristic time is Q, the quality factor of the cantilever. I will explain what the quality factor is. The period of the resonance of the cantilever divided by pi. So after this time, this transient will disappear, and then we have the steady state solution. What is important to realize is that all AFMs that operate under the assumption that we have a steady state solution. So all the term, this term in particular, has disappeared. For the mind of the microscope, only this term exists. Of course, if this transient term has not disappeared in reality, then we are going to have a problem with the image. So this needs to be considered for the proper interpretation of the data. So this is how the AFM operates in the amplitude modulation mode, where we have this tip that touches, in this particular case, a protein, and you do this imaging while keeping a constant amplitude. Now, this is a paradox. The operation of the AFM in dynamic mode is controlled by the tip sample interaction. And what we want to learn is just the expression of the tip sample interaction. However, in dynamic AFM, actually the force is not a direct observable. So the force modifies the dynamics of the cantilever, but we cannot measure that directly. So actually, in order to get the force, what we have to record is the dependence of the amplitude of the oscillation as a function of the tip sample distance, the dependence of the phase shift of the oscillation as a function of the tip sample distance, and apply an integral, a method to integrate those functions, amplitudes, and phase shift. And from that integral, we get the force, what gives us information on the properties of the interface. Let me just mention two items that have been paramount in order for the evolution and development of force microscopy. One was the development of integrated microcantilevers and tips based on semiconductor technology. And this, the first AFM that were developed, they didn't have this cantilever. They have just tips glued into a aluminum foil. So this was a major breakthrough by Calvin Quaid and Gressner that really enabled the commercialization of the AFM. And another discovered was the use of an optical beam deflection method to measure the changes in the deflection of the microcantilever due to the forces. This was a very robust and a method with a very high signal to noise ratio. And that was another major breakthrough that paved the way to have commercial AFMs. The tips are paramount. The molecular finger in the AFM is paramount for the spatial resolution. So we have, the tips are usually made of silicon nitride, silicon oxide, and actually the ones that give you better resolution on on biology are made of carbon diamond-like tips with carbon fibers. But this is an SEM image of really a very high spatial resolution silicon tip. You can see here that at the end the tip is of the order of, I would say, 20 nanometers. Let me just say, explain the relation. The AFM I mentioned is a mechanical microscope. We measure mechanical forces. We sense mechanical forces. So the forces also control the spatial resolution. We understand in an intuitive manner that the size of the molecular finger, the size of the tip, will control the spatial resolution as well. But it's less obvious to realize that the force that we apply on the sample is also a factor control the spatial resolution. So let's go from observing single atoms in ultra high vacuum, like this, adsorbate thin atom, to get sub-nanometer resolution of membrane proteins, to get 2 angstrom, 3 angstroms nanometer resolution, 3 angstrom nanometer resolution in single antibodies, to get 100 nanometer spatial resolution cell. What you could see is that when we go from a stiff material to a very soft material that is the cell, there is a decrease excuse me, in spatial resolution. Why is that? Actually, this is a more I think a comparison that reflects better. This is a high resolution image of antibody IgM pentamer in water, in liquid, and this is a high resolution image of a membrane protein, also in buffer. If we were able to get the same spatial resolution of a single protein, like in the membrane protein, we will be able to see something like these domains here that we are not able to see. Thus, that the information that we are getting is that it's easier to get with AFM resolution in stiff materials than in soft materials. Why is that? Excuse me. The reason is because we apply a force that produces a deformation in the material, and this deformation has associated a contact, a lateral extension, and we can use contact mechanics to find the relationship between the lateral resolution and the force that we apply, and the properties of the material. So, if we have a stiff material of 10 gigapascal, if we apply a force of, say, 1 nanonewton, we can get a lateral resolution of 1 nanometer. However, if we go to a soft material of 100 megapascal and we apply a force of 1 nanonewton, our spatial resolution suddenly has gone worse to 4 nanometers. So that tells us that really that explains why it's easier to get higher resolution on stiff materials than on softer materials. And if one wants to get very good spatial resolution on soft materials, proteins, polymers, cells, one has to go to very low forces. So this is an important point that explains the paradox why one can get atomic resolution on a stiff material and not on a soft material. Let's use these density functional theory simulations to really see how by increasing the interaction we got from very atomic scale interaction. If we increase the interaction like here, we got that the lateral extension goes affect other chains, and in this particular case, we just see that the extension goes higher. So that's an illustration that really the force is a paramount factor in the spatial resolution of the AFM. However, there are other factors that contribute to the spatial resolution. At the end, the ultimate spatial resolution that you can achieve in the AFM is controlled by the thermal noise. Usually, the experiments performed by AFM are done at room temperature. So we have a thermal noise due to that. The surface roughness is another factor. The properties of the sample we already showed was another factor. The radius, certainly, and the force. Let's, well, I think I can skip this. So let's see how the thermal noise affects the resolution. This is just the thermal noise of the cantilever in the deflection. And you have here the Boltzmann constant, the temperature, the quality factor, the bandwidth of the cantilever, the resonance frequency, and the force constant. But you can see that really there are some cantilevers with their parameters where you can get that the noise, the thermal noise deflection is just 10 picometers. So these tell us that indeed we can achieve, in principle, we can achieve sub-angstrom resolution with the AFM, which is good to realize that this could happen. Well, this is another explanation of what is the lateral resolution for the formable materials. And actually, the lateral resolution depends on the tip radius, and also depends in the high difference of the object that you want to separate, and also with the noise that you have in zeta that was calculated previously, but we see that the thermal noise is already very small. And then we saw that the spatial resolution depends on the compliance or the material properties, the Young modulus of the sample, but also on the applied force. And actually, this is a commercial cantilever. You can plug the parameters and calculate the minimum force obtained by the thermal noise, and you see that the minimum force that one could detect with AFM is of the order of 3 piconewton, but that's has a very, very, very small force. So in principle, because, for example, the force between the equivalent force between a covalent bond is of the order of several nanonewtons. So we are 3 orders of magnitude lower in principle. That again enables us to get sub-angstrom spatial resolution. So now let's go, after this introduction, on some fundamental properties of the AFM that work either for vacuum, air, or liquids. Let's try to go down a little bit more to the focus of the colloquium, that are solid-liquid interfaces. So what happens when we operate the AFM in liquid? So what happens are 2 things. The first thing is that the cantilever displaces the liquid when it oscillates. And that displacement has associated 2 things. One is a transfer of momentum of the cantilever to the liquid molecules. And this is what gives rise to the Q factor, a decrease of the quality factor of the cantilever. In addition to that, the displacement of the liquid creates, liquid have some viscosity, and the displacement of a liquid creates some dissipative processes between the liquid molecules. So we have some dissipation associated to this viscosity. And those effects really are going to have an influence on the properties of the AFM and the cantilever. For example, this is how the resonance curve of the cantilever changes when we go from air to water. So what we see that in air, the resonance curve of the cantilever, so the dependence of the amplitude of the cantilever as a function of the excitation frequency are narrow. And when we go to water, or to a liquid, it gets broader. What does it mean numerically, quantitatively? It means that the quality factor of that cantilever was of the order of 100 in air, and now goes to 4, a small quality factor. So that's what happens when we go operating liquid, that the quality factors are of the order of 1 to 10. Also, this is reflected as well in the phase shift of the cantilever. In water, in air, sorry, you have a very sharp transition, a resonance around 90 degrees, and in liquid, you have a smooth transition. So that's one thing. But there is something else. If we have the same cantilever in air, and now we take measure the resonance curve in water, we got the broaden. I explained that before. But if we look into the frequency scale, we see that when we started in air, the resonance frequency was around 20 kilohertz. When we just introduced water in the AFM chamber, we saw that the resonance frequency of the cantilever went to 4 kilohertz. So we a decrease of a factor 5. Why? Well, this is because the cantilever is the same, but in an effective manner, some mass of some fluid is always, some liquid is always attached at the cantilever when we put in liquid. So when the cantilever moves, has to move this liquid that is always attached to it, that is like another mass. It's like in an effective manner, it's like if the cantilever has weights more because of this. And because for our harmonic oscillator, there is the relationship between the resonance frequency, the force constant, and the mass is this. If you increase the mass, means that you reduce the resonance frequency. So that happens and is well explained, is something that we should expect. But there is something more. we mentioned that the Q factor of the cantilever decreases when we go from air to water. But if we measure, like in these simulations, the quality factor of the same cantilever as a function of the separation to a flat surface in water, we observe that the cantilever gets reduced. And this is not because of this effect. This additional reduction of the cantilever when we are getting close to the surface is because we squeeze the cantilever and the tip squeeze the liquid between the two surfaces, the surface of the tip and the cantilever and the solid surface of your sample. And that originates an additional viscosity effect that reduces the cantilever. Well, why I mention all of this? Well, I mention all of this because this is part of the complexity of operating an AFM in liquids. And it's the knowledge that one needs to have if one wants to improve the instrument to really to operate at high speeds and atomic scale resolution. So those concepts need to be needs to have it in mind in order really to get dynamic processes at atomic scale. Again, those things that I mentioned could be calculated in an effective manner, and there are models to calculate the added mass of the cantilever as a function of the density of the liquid and the properties of the size of the cantilever, and also there is a way to calculate the quality factor or the damping as a function of the density, viscosity of the fluid, and the mechanical size of the cantilever. This is just to mention that could be calculated. So now let's go a little bit a step further in the complexity, but we will reduce later. So I don't try to scare anyone. Actually, to use the Newton equation to describe this object in liquid looks something, well, that at least need to justify clearly and to explain why is that possible. And that's true. The actual equation of, or the best approximation to describe the equation of a microcantilever tip is just the Euler-Bernoulli equation, which is this thing here, which is a bit more complex than the Newton equation. Where we have all the terms here. We have here on this side, we have the inertial or the equivalent to the inertial term. We have here the equivalent to the deflection of the cantilever and the internal viscosity. And here we have the forces, the external forces for the citation of the T-sample force. And here we have the external viscosity. What is interesting to know is that this continuous equation that tells us that the cantilever has a large number of resonances, not only one, just several, many, we can really find that there is a way to discretize this equation and put it as a system of equations, one per mode, which in practice means that because the resonance frequencies are far apart, in practice, it will mean that I can still describe the cantilever as a Newton equation, just putting carefully the effective mass and the Q factors of the cantilever. So just all this complexity just was to say, yes, the equation of the microcantilever and the tip is not the Newton equation, the best approximation, but we can approximate that as a system of equations for the different modes, and eventually, because the modes are far apart, we can use the one that we are operating. And this is just the resonance frequencies of this cantilever in water. You see, this is the thermal noise spectrum, so there are not forces applied, no driving forces. It's just we record the power spectral density of the microcantilever, and you see that the thermal noise is exciting the resonance, first mode, second mode, third mode, fourth mode. We can make a zoom in the first mode that oscillates like this, or we can make a zoom in the second mode that oscillates like this. Why do I mention this? The important thing is that even, well, just to realize, the cantilever has many frequencies, and we can measure that. And now, what we can do is to decide to operate at this frequency, or this frequency. And we decide that when we just tune the cantilever to that resonance. And when we decide that, then we can apply the a Newton equation for that resonance. So that's, yeah. And well, there are some complexities here, but at the end of the day, all the resonance frequency, force constant, optical sensitivity, quality factor of the microcantilever for a rectangular cantilever are related. So that's good. So there is complexity, but has been solved already. One thing that I would like to mention, because sometimes it's not so clear, is that each mode has a resonance frequency, has a quality factor, has a force constant. All the modes have the same mass. However, if you consider a cantilever, this cantilever static, that as I said has many modes, in the static approach that we just deflect with a force, the force constant of this cantilever is just the composition in series of all the force constants of the modes. So the static force constant do not coincide with any of the force constants of the different modes, but is very close to the fundamental mode. So that's why sometimes one measures the static constant and uses the operation of the AFM in the fundamental mode and consider that has the same force constant. It's not exactly the same, but close. Now, other thing that explains part of the complexity of operating an AFM in liquid is that the way we excite the cantilever matters. So through the history of the AFM, different ways have been developed. One is the called acoustic method, that you move the piezoelectric. Then people coated the cantilever and apply a magnetic field to excite the cantilever at the tip. And later, it's just we use a laser, we change the power of the laser, oscillating laser, and changes in the thermal properties of the cantilever due to the heating makes these things vibrating. So actually, the best methods to excite the cantilever are photothermal and actually or magnetic. The magnetic is no longer used because the magnetization process degraded in solution, so eventually was not applied. So the photothermal method really is the one that produces resonance curves that are canonical. So you can really compare them with the one that are obtained in theory. However, when you excite the cantilever acoustic and liquid, sometimes what happens is that one would get a very noisy resonance curve. Why is that? Because the acoustic method just move not only the cantilever, but move the cantilever, move the fluid, and also the fluid rebounded in the walls of the cell and interact again with the cantilever. And really, you compare with the same instrument, the resonance curve in photothermal, canonical, and in the acoustic method, you see this difference. So actually, if any one of you is going to buy an instrument, I would suggest for operating liquid, consider use the one that has a photothermal excitation method, because you will get data that could be easily interpreted with the field. This is just an animation. Sorry. This is the photothermal excitation. This is the detection of the cantilever, and you see how when we move the position along the cantilever axis of the excitation, how the excitation happens. So there are some position that is the optimum to amplify the excitation. So that's something that when you do the experiment, you need to really to figure it out, which is the best place to excite the cantilever in order to magnify the amplitude. Well, now we are doing the experiment. And this is what I mentioned, that when we are moving the cantilever in liquid, when we are approaching to the surface, actually the liquid wants to prevent the approaching, so it opposes a force. And when we just pull back the tip, the force is in the opposite direction. Well, one has to know that this force, actually, we can use the Reynolds numbers that tell us about the viscosity of the medium and the condition. We see that the Reynolds numbers in AFM experiments are very low. So that means that these hydrodynamic viscoelastic forces are linear. And actually, this is an example of getting 4 distance cubes at different speeds, 2 microns per second, 8 microns per second, 20 microns per second. You see how here at very low speeds, there is an overlap going in, going up. When we increase the speed, we see that the cubes start to separate, and then here you see fully separated. So actually, when you want to do precise measurements, you have to get this calibration of the drag force. So this is what you have initially when you didn't correct for this drag, and when you correct for this drag, you remove it, and then the interaction that is left is the proper interaction due to the properties of the sample. So this is something that you need to be aware. Bueno, the properties, the cantilever calibration, again, is paramount because the proper cantilever calibration is what will give us, allows to the measurement of properties of the interface of the material. So the one wants to calibrate the force constant, the quality factor, and the resonance frequency, and the optical sensitivity. The optical sensitivity is for the photodetector and tell us how many volts changes in the detector are associated to nanometers in the displacement of the cantilever. Well, here I mentioned some references to cantilever calibration. So the way we do, at least we do, the cantilever calibration nowadays is as following. First, we calibrate the sensitivity of the photodetector using a stiff, clean sample, mica glass, to get the optical sensitivity. Once we get the optical sensitivity, we get the power spectral density of the mode, and we feed that power spectral density to the Lorentzian function. And then, and from there, we get the resonance frequency and the quality factor. And then we apply the equipartition theorem to get the force constant of the cantilever. So this is one way to do it. Nowadays, well, this has the problem that you have to get this 4 distance curve that could modify the cantilever. Now there are contactless methods that have been calibrated by measuring cantilevers of the same type, and then you really have an expression where you have to get only just the quality factor of your cantilever in Earth, the resonance frequency in Earth, and then you, for this type of cantilever, you have some reference values obtained by interferometry and Q reference and frequent reference. They are tabulated that for that cantilever. So just you measure this, and you get the cantilever. And then again, for the higher modes, again, you have a scaling law where some people has already, for the same batch of cantilever, has done an extensive analysis using optical interferometry to measure those values, and then you plug what you measure, you get the coefficient from those tables, and you get your force constant. So in the early days, it was complicated to calibrate the cantilever properly. Now it's done. So now we have just, this is the scheme of the force relevant in liquid. We have van der Waals forces, electrical double layer, hydrodynamic forces, adhesion forces, short range viscoelastic force, short range repulsive forces, viscoelastic forces. So this is an equation that could describe the cantilever, including the electrical double layer forces and the short range forces and the van der Waals forces. So now comes this point. The point is that in order to get atomic resolution, we need to have a molecular finger. However, van der Waals forces, electric double layer forces are long-range forces that are going to compete with that. So somehow we need to screen those forces if we want to get atomic scale resolution. So then this cartoon illustrates this competition between short-range forces gives resolution and long-range forces that could be there because there are charges that decreases the resolution. And actually, one of the earliest breakthroughs in imaging came by the group of Andreas Engel in imaging biomolecules, that they realized they measured the force distance curve on this protein, outer membrane protein F, as a function of the molarity of the solution. So they start with a 20 millimolar potassium chloride, and you could see, this is the go in, go out, you could see a long range force, because when you are approaching here, you start to feel some repulsion, and then the tip moves 20 nanometers, which is a lot, and you are increasing the repulsion until you get in contact. So with this long range force, one cannot get atomic scale or nanometer resolution. When they were increasing the molarity, they saw that the long range force eventually decreased until they reach this value for this protein. It will depend on each protein, 300 millimolar, where the force distance curve going in and going out overlap. And this is the optimum region to get atomic scale resolution, because you have screened all the long range forces, and the remaining forces are the short range repulsive forces that will give you the resolution. So this is and that enabled them really to get at that time nanometer scale resolution, and that was a breakthrough for all the people doing high spatial resolution imaging of biomolecules, that you need to tune the molarity, the ionic strength of your buffer solution in order to really to get to the molecular finger to work. And that really, these some images that happen after that of nanometer spatial resolution in different proteins, DNA, where you see really the structure of the DNA, and here even you see the DNA, and here the atoms of the mica, that where the DNA was. And here is another example of imaging with atomic resolution, the dissolution, and this particular was calcite. This is the rows of oxygen atoms as a function of time, and you see how the top plane, which was this, is being eroded, is being dissolved as a function of time, and we get we dissolve two planes actually, and we reach this one. So this is an image that was obtained by the group of Takeshi Fukuma, and was captured at a rate of 0.5 frames per second. So for each frame, 2 seconds. So that was obtained with high-speed AFM that I will show later. Here is another image when people just included all the concepts that I explained, where you get atomic scale resolution of rubidium ions on a mica surface. And then they discuss the different configuration, either ions were isolated or in a row, as in this image. Another example, this is the study of the electrical double layer of a gibbsite as a function again of the molarity, and you see by the group of Mugele, and you see how the surface was changed gibbsite in water at 10 millimolar molarity. You see this double arrow. At 100 millimolar, you see a different structure. And then they use some density functional theory in order to explain how the structure was influenced by the molarity. So the AFM, this is important to realize, the AFM gives you resolution, but sometimes you need a backup of the theory to understand really the feature. But those examples explain that really when you have tuned the parameters, you can get atomic scale resolution and study that as a function of the molarity. So just in the last few minutes, just the advanced methods. The advanced methods are high-speed AFM and three-dimensional AFM. High-speed AFM. Okay, the question is that at the end, what we'd like to get is atomic scale resolution at high speeds, because we want to get dynamics of the interaction of atoms, molecules, proteins in real time. So in order to do that, we need to understand what are the factors that may limit the speed of the AFM. So the factors are, for one thing is this, the transient term that I explained earlier. The other factor is that we need to track the changes in the topography of the system by using a scanner that has another delay. We have an electronics feedback circuit called proportional integral differential that also causes some delays, and also we have some parachuting effect. So Toshio Ando, that was the pioneer, developed the compute the time delay associated to each of all those factors that were expressed there, and found out that really, let me just go through without explaining all the details, but you see that all of them, well, most of them really depend of F0. F0 is the resonance frequency of the cantilever that you are using for imaging. So at the end, the important thing is that in order to improve the speed of the AFM, we need to make this T0 very small, and that can be done by increasing the resonance frequency of the cantilever. And actually, this was the key point for the advent of high-speed AFM. So this was, let's say, a regular cantilever, and at the same scale, this is one of the cantilevers that are used in high speed, even they are really smaller ones. And this is just a comparison between what means imaging at high speed on the right, standard speed. So you see the high speed gives you the same spatial resolution, but while you are still 1/4 of the sample or 1/3, you have imaged the sample here 10, 20 times already. Of course, in this case, there is nothing to be gained because the sample was set already. But here, this is an example by sorry, I want to keep. So this is an iconic sample of Toshio Ando's group, just showing how myosin 5 was walking along of actin filament fiber. And actually, this in molecular biology explain how this process was done and was enabled by just the high speed AFM. This experiment was performed at 7 frames per second. And you can see, I hope everybody can see here the myosin, that this is like this B, 2 legs. Another example, sorry, let's move on. This is another example of just the early stages of the polymerization of collagen. Collagen is one of the most abundant proteins in the extracellular matrix in our body, and you can see, you can follow here topographic elastic modulus changes, and you can see really how the monomers assemble and you grow the structures. Well, I am not explaining many details about the processes because I think just to give the idea that really you can keep a very high spatial resolution and tracking processes in real time. And this is another example of a membrane protein, bacteriorhodopsin, that is a proton pump. How the protein interacts with light by opening the pores or closing it. So you see, dark is no light, you open the protein, and when we shine light, green light, you close the trimers. Let's do it again. You close when you, and you open when there is darkness. So this is just a molecular view of this proton pump under the effect of the light and how it was recorded in real time. Again, this image was obtained at 1 frame per second. And the last topic in advanced AFM methods in liquid is just three-dimensional AFM. So AFM, what I show, all the images that I showed before, what show is what is a surface and how ions are on top of the surface, or what is the structure of the surface. So with the three-dimensional AFM, what one would like to see is the volume of the surface, how the liquid molecules reach the surface, how they evolve, how they organize in the three-dimensional space. This animation illustrates that. So we have our vibrating tip, and at the same tip that vibrates, it is displaced in the volume of the liquid near the surface. And if you do apply all the concepts that I explained to you, the idea is that the passing of a single ion or solvent molecule would modify this dynamic parameter, resonance, frequencies, amplitudes, phase shift, and we were able to detect it. So that's the philosophy behind the concept of three-dimensional AFM. This is a real image of water on a mica surface. Again, this is the image. So here you can get planes in all the three directions. And actually here on orange is the mica surface, and these white strips are 3 angstrom width and reflect the organization of the water above the layering of the water above the mica surface. You see 2 layers, 1 and 2. And then you make a cross section in a plane perpendicular to the surface. You see the ions absorbed on the surface. These are potassium ions, and you see the water molecules here and there. Well, of course, by the AFM images, one can only claim that you have very high spatial resolution, but you cannot claim what is the source of that resolution. So you have to use theory, either DFT or molecular dynamic simulations. And in the theory, you can plot independently the density of the different components of the system as a function of the distance to the surface. And just by matching the oscillations of the different components, when what you observe on your images, then you can relate to these oscillating stripes to the water, because it's the only parameter that in the simulation oscillates as a function of time. The density of the ions do not oscillate, has a peak on the surface because they get attached electrostatically, and the chlorine ions are expelled from the surface. And now we are going to show you how this three-dimensional AFM enables to see the organization of the water molecule, but not on the surface, but just above the surface. So this is really the position on yellow, the micas, the potassium ions absorb. We can get the cross-section, and you see this is the potassium ions plane, and you see here the position of the potassiums here. Now, if we move further up from the surface, we go to this layer of water, and we see here these hexagons that are the organization of the water molecules that are surrounding here the potassium ions that were underneath. If we move again further up, we see another lattice of water molecules further from the surface. And if we are related the position of these water molecules with respect to the potassium ions on the surface, just 3 or 4 angstroms below, we see that they lay on top of them. So this is the real image. And we did that also for other molarity solutions. You can get more volumes, and you see really other structures and periodicities just at different distances. So just three-dimensional AFM offers you the capability to image volumes of solid liquid interfaces with atomic scale resolution in the 3 spatial coordinates. Well, this is an example of the same technique applied to an ionic liquid under an electrochemical conditions with 3 electrodes, and just seeing again the distribution of the components of this ionic liquid, the mean and the TFSI, as a function of the different voltages. Again, in order to interpret the image, you need theory in order to help with interpretation. And the last presentation is how this thing works. Well, this thing works with atomic resolution because we have a molecular finger. What is the molecular finger? Because actually my tip is something like this. The molecular finger at the end is done by a solvent molecule. In case of water, a water molecule that is attached at the end of one of the atoms of the tip, and this solvent molecule is the one that is going to act as the effective tip to image the solid liquid interfaces. And with this, I finish my presentation. I try to convey well, the complexity of imaging solid liquid interfaces with AFM. I try to explain that there is robust methodology behind that was able to overcome all the complexities and difficulties associated to the operation of the AFM in liquid. And yes, I thank you for your attention.
Thank you so much, Ricardo. It's an excellent talk, and I think it was a very good introduction for a lot of people who are not in the AFM field and the force microscopy field specifically. So we're open to questions, and the audience, as usual, can raise their hands, or you can just ask questions directly. Maybe I can start by asking about the few last slides about your three-dimensional AFM, because this seems to be quite interesting. It's something that's been around for a while. So first of all, do you see the domains of potassium ions, say when it's adsorbed somewhere? Do you see like there are regions where you have no adsorption and there are islands of adsorbates forming somewhere?
Yes, that's happening. Yes, the absorption of the potassium ions is not uniform. There are islands where they are gathered gatherer, and there are other regions where are deserted of adsorbates. Yes, that happens.
So in other words, if you have a complex electrolyte or a complex liquid system with a number of different molecules, maybe ions to absorb, you can see how this co-adsorption is playing on the lateral scale.
Yeah, in principle, yes. But Andrew, it's not going to, yes, but you need to really to do the experiment, to tune the parameters properly in order to be able to resolve the species and separate the species in the way you want. Okay, yes, it can be done, but it's not going to be, well, the scientists have to do some work to do it, to get it there.
Okay, and about the time of the measurements, I noticed that it's over 100 seconds per one 3D map.
Yes.
So does it mean that, is it that difficult to keep the sample intact during those measurements? Because I can imagine that it's a lot of time. At the atomic scale, it's a huge time. So you have to be extremely stable in how you image it.
No, but maybe I didn't understand the question, but actually the stability of the instrument, at least the one that we operated, when you keep the temperature of the surrounding constant, is very good.
I mean, so commercial instruments can reach this accuracy over long time scales, no problem.
No, the state of their instruments can get it there. Okay, you need to really to keep the temperature of the AFM stage constant.
Okay. Just reminding, you can ask questions, please, anyone, if you have any. And I have also quite a number of other questions. So you mentioned at the beginning the amount of force that you can impose on the surface and how well you can control it. When you image the surface layers, how can you be sure that you're not perturbing it? Do you have to do then later some calculations about what kind of force you really could impose with this, or you have a pre-calibrated instrument to the extent that you absolutely know how much you perturb it?
Well, no. Actually, the forces that you apply are very small. You can see here. These are a real force distance curve. And you could see here that for imaging the second layer, the force would be, I think here is like 30 piconewtons or so. So yes, we apply very small forces. How we control that? I didn't mention properly because the amplitude that the tip oscillates is 20, 30 picometers. So you have really to apply very small oscillation amplitudes. If we were not able to do that, so just the tip is just the molecular finger oscillating 20 picometers. You mean this is sub-Armstrong oscillations. So you have to tune all your equipment in order that you just oscillate these 20 picometers and you can measure it. So that's where the point, the difficulty lies.
So as long as you know,
once you have done that, you can see that the results are very reproducible ones after the others. So
I see. Yeah. We have a question from Ahmed.
Hi, Ricardo.
Hello. I have a question related to the topic. Can I use the AFM method to measure the size of nanoparticle deposited on a surface of solid material?
The size of what kind of particle?
The size of a nanoparticle.
Nanoparticles
deposited on a surface of solid materials.
Yes. I don't see any difficulty whatsoever. I mean, maybe I didn't understand the question.
So I mean by my question, I can use this method AFM to measure the nanoparticle size. deposited on a surface of solid materials. I want to know the size, identify the exact size of nanoparticles was deposited on a surface of solid materials.
Okay. There is this. About the accuracy of the measurements.
Yeah.
In terms of the height, the AFM can give you the proper height of the nanoparticle with sub-angstrom accuracy, okay? So very good. In terms of the lateral size, is another issue, because the imaging of the AFM is always a convolution of the tip size and the nanoparticle size. So if the tip and the nanoparticle are of the same size, then we are going to have a problem, okay? If the tip is much smaller than the nanoparticle, everything will be fine. But if they are comparable, then the accuracy in the lateral measurements are going to be diminished. The vertical, in principle, is not an issue, but the lateral could be an issue.
Okay, thank you.
Thanks, Mohammed.
Hi everyone. Thank you very much, Ricardo, for this great talk. Actually, I had a very interesting idea. I just wanted to ask you, what is the reason that we require the bi-modal in creation of this 3D map of water? To be straightforward, I want to know what really is the idea behind this 20 picometer oscillation requirement there? I mean, we could also, if you have enough sensitive cantilever, we could also map the water layers just by force distance curve measurements. So basically a static one, or as you know, this quantitative imaging.
Yeah. Well, no, bi-modal AFM could be used because you can get gives you more properties at the same time, but you don't need to use bi-modal AFM to get three-dimensional AFM maps, okay? So the answer to that question, you could use bi-modal, you could use amplitude modulation. So it's not needed. Bi-modal is not needed. It could give you some other things, but it's not needed. The second question. The second question is deeper in a sense, because it's dynamic modes versus quasi-static modes. So it's a deeper question. So is there any difference? Well, the answer is yes, there is a difference. Which is the difference? The difference lies in that dynamic modes are resonance. The signal-to-noise ratio is enhanced by the resonance effect. This fact that the mechanical system absorbs energy, maximizing the absorption of energy at a given frequency, the resonance. So that is unbeatable already, okay? So for the same signal-to-noise ratio, the dynamic mode will work better. Of course, if you really improve or reduce to zero the signal-to-noise ratio in a quasi-static mode, you could measure the things as well. But it's always going to be harder. So it's always going to be harder. That's it.
Thank you. How come?
Yeah, thank you, Professor Garcia. I was going to ask if you have you tried to use this AFM technique with in situ electrochemistry measurements?
We are working on that. Actually, yes. The answer is yes. I didn't present the data because I wanted to show something more general, not only my work. But yes. Do you have some specifics?
Because I'm from Shandon Batteries Group, and we used to do that, but now we are trying to reproduce that. But I'm not working on that project. One of my lab member do that. So And it seems to me that it is quite difficult. I was wondering if you encounter any difficulties or there's any like key points that we need to pay attention to, something like that.
So let's see. You mean to this work? You were asking a question about this work.
Which work?
No, in the slide, can you see my slide here?
Yes, I can see your slide. Okay.
Is your question related to this or not?
Maybe I can rephrase the question. I think I quite understand. The question is, when you move from a regular surface liquid interface to an electrode liquid interface and you apply bias to the electrode,
yes.
what level of complexity do you have to go to, and what type of
No,
problems
yes.
can you encounter?
That's no, I said the level of complexity increases in the following. What I explained, like in this image here, or this image here, everything was explained in terms of changing mass densities, the distribution of the mass of the solvent or the water. When you have a complex electrolyte and you apply a voltage, then you have to consider two things: distribution of mass, distribution of charges, and see the forces associated to distribution of mass and the forces associated to distribution of charges. So that makes things more complex, the interpretation. So you need, it can be done, but you know, you need to be able to separate the influence of the charges from the influence of the masses in the force and in the images.
Yeah, and in terms of like the experimental setup, is it like pretty straightforward to incorporate this in situ electrochemistry?
Yes, I would say not major issues. No, it's not difficult to put the 3 electrodes. I think the question probably is what kind of electrode do you want to put? That could be more difficult, you know. For the AFM could be there are some electrodes easier to handle than other electrodes.
I see.
But let's say if you would affect that graphite could be a reasonable electrode for simulating some energy storage in batteries, and we could put the ionic liquid, or it could be that could be done in a straightforward manner. Now,
okay.
if you have, you know, a porous electrode, then for the AFM that would be more difficult to handle.
I see. Thank you, Professor.
You're welcome.
Next, HX1.
Hi, Ricardo. Thanks for the great talk. I'm also interested in the 3D AFM in your last few slides, because I think the way you're measuring the double layer structure is kind of a destructive method, I would say, because in addition to the solid liquid interface, you also create a cantilever liquid interface, right? And also you're inducing like forced convection near the solid liquid interface. So how much do you think are you changing the solid liquid interface you want to probe?
Well,
are you changing it a lot?
No. You need to realize these things. The first thing, maybe I didn't emphasize, or maybe Andrew wanted to ask, but anyway, the question is, or somebody, the question is, the amplitude of the oscillation is just, let's say, 50 picometers. 50 picometers. The size of a water molecule is 3 angstroms, which is like 3 times or 4 times larger. So you need to factor this. So you are, yes, you are moving something, but you are moving the fluid 3 times, you are moving the tip 3 times smaller than the size of a water molecule, or 4 times. So yeah, you can affect, but I would say you are affecting very little.
I see.
I mean, you need to factor this, that really this tip here, this thing here, when I say it oscillates, yes, but how much? It oscillates 50 picometer. 50, you could, you know, these are the 3 angstroms, so you are 50 3 angstroms is just 300 picometer. So I could gather that really the interaction with that interaction is not going to disrupt the water molecule. That's one thing. Okay. The other thing is that we compare our data with simulations, with molecular dynamics DFT simulations, and they agree. So in principle, that's solved. Of course, if you don't do the things properly, you can damage many things, but yeah.
Okay, thank you.
Thanks, Ricardo. A question from the chat that gets us back to electrochemistry. I think this is a very good one, because it probably you will say no, but I'm curious about what do you think in the future, if it's possible. So the question is it possible currently in any way to observe the position of a molecule that undergoes electrocatalysis, say oxygen, or maybe it's CO2 reduction? So you see how CO2 transforms into CO under potential, or it's fundamentally too far in the, so it's just too complicated.
Yeah, you say it's too complicated. Let's say to see. I would say you just you put the sample of CO2 that is too small. You use, let's say, a larger molecule. I would say a larger molecule would be more feasible. You just use these very small molecules. I would say that's very, I don't see it clearly. It has to be for a larger entity, macromolecule. Yes, I think those things are feasible. For that one, you know, that small one of, I think is very, yeah, I don't see clearly.
I see, yeah. So we know that from UHV experiments, AFM inside the UHV chambers down on molecules, you have to be working with large molecules to see these differences. Even there, I think in liquids, it's even worse, right?
Yes.
Okay, we have a few more questions. Anas, do you want to go?
Thank you. Hello, am I audible?
Yep, we can hear you.
Hello. Yeah. Thank you, Professor, for the insightful talk. And I actually am a little bit confused, not with your talk, but what I am doing. Actually, I've been assigned to work with electrochemical AFM for oxygen evolution reaction. And I've been reading some literature, and I myself want to do operando electrochemical AFM. And I just want to know how can I be sure that what I did with AFM, it's operando? For example, what I'm asking is like, do I need to go really slow imaging with the AFM or very fast imaging? I am not sure about that. I really could use your view on it. For example, if we look at the literature, some people actually use really slow scan rate, like 5 millivolt per minute, which makes it, and they are taking AFM image very slowly, like 10 minutes to acquire one single image. That means they are changing only 50 millivolt during one AFM image. So is it the operando AFM, or it would be operando if we do a really fast image of AFM, like in, let's say in 2 or 3 seconds that you have shown in your presentation. So it's really like a confusion for me. I'm new in this field. I just started my PhD, so it's kind of a question, like just a confusion that is in mind. So,
yeah, I guess the answer to that question, I would say, lies in the time scale of the effect that you are trying to induce or to observe.
Yes, I was about to add this as well. So does it have to do with the time scale as well? For example, if you look for the electron transfer, and if I'm not wrong, it's nanoseconds scale.
Yeah.
So how does it relate? Yeah. How can we relate the AFM imaging with the electron transfer time scale? Is it possible?
You know, at the end, the frequencies of the AFM usually are in the highest 10 megahertz, something like that. So everything that happens at faster rates, the AFM cannot respond.
Okay.
So there is no, in that sense, the AFM is a mechanical system. So that's, well, has some strengths and some weaknesses in the sense of the frequencies at the end are more, the limit are the megahertz or something like that regime.
So I basically, like, I'm always concerned with the changes that happen with time, not with volt applied potential. So you know, if, like, for example, if you are in the, like, you started imaging your catalytic surface, let's say a thin film, and you imaged already a part of your thin film, but some changes are happening after you image it, and you get that change, you image that change in your thin film morphology when you go for the next applied potential. So I think it's kind of misleading in some sense, because I hope I'm clear to you, because it's a kind of a dilemma for me. So I'm not really sure, is it a right way to do it? Because
I
also,
think you have to use a scan rate, and you apply a voltage, you know, that let's say at the end you want to image everything that has happened has to be observed during the time that you are imaging.
Yes.
So that if that's not the case, then you are not getting properly the information, or you cannot study that phenomena with the equipment that you have.
Yeah. So more reasonable, what's your opinion about, like, more reasonable would be if we just image the entire area of interest in, let's say, 2 or 3 seconds, like with a very fast AFM imaging mode, or it should be slow? That's actually my question.
Well, initially, I would say, in principle, the fastest that you could image would be the better. But what is the issue? The issue is that you image fast but without any controls, then you are not going to get anywhere. So you need to see if really you can get an image as fast as you can, but the image is meaningful, is, you know, has the proper signal to noise ratio, so on and so forth.
Okay.
Thanks, Anas, for your questions.
No, thank you.
Maybe I can also get back a little bit to the tip sample interaction. Ricardo, what would you say? Do people do experiments with functionalized tips, when they mount a molecule, a specific molecule, the tip that can survive the liquid environment, and maybe this way improve the chemical sensitivity of that mechanical interaction?
Well, certainly in many biological experiments, people use functionalized tips. Sure. For looking for some specific ligand effector interactions. So that is definitely the case. More or less in electrochemical environments, I mean, I have seen some attempts to do that in more electrochemical environments, but they had not been so successful, I would say. So,
what is the reason why it's is it just because the preparation is so difficult, so you need to have enough experience to really prepare such tips, or it's just we're not there because there are other things that we have to work on?
Well, I think in part, you know, for this molecular biology experiment, the system works because the chemistry is there. Sure. And then you don't apply a voltage when you are doing the experiments. So you are like fission. No? You have a ligand, you have the effector, and you are going to meet them. So no issues there. But when you are working a more electrochemical or chemical environment, then the chemistry of the tip could change the tip itself. Mm-hmm. And then the imaging is going to change it as well. So that's what is really is a limiting factor in that sense.
And can you control? I think it was this tens of piconewton precision and force. You can in principle even control the chemical reaction, right? So you can bring the molecule on the tip in the liquid phase to the surface and induce a chemical transformation at a given distance. So in principle, you can see how this chemical reaction is likely to happen under different conditions, for example. Is it something that is
I think they could, yes, with the proper controls, that could be attempted, yes.
Okay, great. Ismail.
Yeah, hello.
Hello.
Just very nice talk. Just thank you for the talk. Just have a question about electrochemistry side, like following the previous questions about it. In case, imagine if you have a very fast nucleation process on the surface, like very fast electrodepositing process that we're gonna probe it with this setup. Do you think it's the kind of the oscillation or the method itself is fast enough to just get rid of like the collision of the tip to this growing process on the electrode surface?
Well, I would say you need to tune every speed. So if the process is faster than the time scales of this whatever process is happening goes much faster than the motion of the tip, you cannot follow it. There is no way. So you need to really to tune that. That's unavoidable. So.
And how do you think that we can kind of tune it? Is it by only like concentration or?
For example, I mean, you can dilute. Sometimes you dilute your samples in order biomolecular interactions. One way to capture the interaction of biomolecules is just to dilute the solution.
I see.
So everything goes slower. So these things could be applied as well.
Thank you. Thank you.
And we have a question from Ren.
Excuse me, I have two questions. First is, if we use AFM to detect the interface between the solid and liquid, there will be an electrostatic field in the electrode layer. It perhaps that the lateral force will disturb the tip sensor. So how to remove the perturbation from electrode layer? And the second question is how AFM can get operando imaging in expected time scale. For instance, in a few seconds or even faster without sacrificing the resolution, because the tip cantilever moving is very slow. However, the surface structure changing is dynamic and very, very fast. So how can we get the operando imaging? That's all. Thank you.
Well, yeah, could you repeat again your questions? I am not sure that I really got them right.
Yeah.
Go on, just please repeat your questions.
Maybe just the first one for now, Rand.
Excuse me.
Yes.
I don't understand you. What do you say?
Rand, can you repeat the first question again?
The first question, okay.
Yeah.
The first question is, perhaps that there will be a late force will disturb the tip sensor. How can we to remove the perturbation from electrostatic layer, because there is an electrostatic field. Maybe there is a force to influence the tip sensor, the tip and the sample interaction.
Mm-hmm.
Okay, no, no, definitely the tip is going to sense, let me see, I am trying to find an example just to explain, instead of using words, using just a slide. And then see if I... This is an example, like here in the top panel, these, these long range interactions are the electrical double layer. That is very long because the molarity was low. With that interaction, that electrical double layer interaction prevents you from getting resolution. Okay. You cannot see the resolution because the interaction is long range, so you are getting information from many different regions of the surface at the same time. So then you don't see really that the interaction is dominated by the tip here.
It's a short range interaction, okay.
So what you have to do, what these people did, and now is done by everybody else that does this thing, is just to tune the molarity of the solution in order to screen the electrical double layer, to reduce it. And then you improve the spatial resolution. So yes, definitely you have this long range electrostatic double layer interaction that is going to perturb and make difficult to get a good image. Yes, that's yes. No doubt about that.
Ricardo, but does it mean that when we do it on electrodes in electrochemical experiments where we want that double layer to be there and we want to study it, then we will be confronted with the same type of problem?
No, no. Well, let's say depends on what you want, because at the end here you can see the extension in the Z coordinate of this double layer. You can see because you are measuring from where it starts and where it ends. So you get that information. Now, the question is, now you also want to see the molecular distribution of the different ions and cations there. Bueno, okay. So in principle, it could be, well, there could be ways to handle that. But we need to devise a scheme to do it. Okay, but in principle, I see solutions to that problem, but it's not straightforward. Okay, it's because we need to isolate it. So actually, what could happen is that usually what could happen is that we could have a signal that over this long range overimposes some small oscillations associated to the changes of your ions there. So that that is really, it could be done. It could be done. Yes, it could be done.
Mm-hmm. Interesting. Thank you.
Okay,
Actually,
thank you. Thank you very much.
I am sorry, but I have an example of that, but I didn't put it here, so I cannot show you actually, because in some of these curves, like here, in one of these curves like this, actually here we have a long range interaction. So but that long range, you know, what has a exponential decay, and then you can fit it. So you get the data, and then you know the dependence of the different interactions. You can remove them or enhance the other. So it could be done. It could be done. The answer to your question is yes.
Mm-hmm.
It could be done.
Mm-hmm. Okay, maybe I will ask a few more questions and we will wrap it up for today. One of them is related to the simulations. So you showed some simulations, but so my question would be, when do we really need to do atomistic simulations, meaning say using molecular dynamics, when we do this atomic scale imaging? Is it important for interpretation of imaging? Because at the atomic scale, a lot of concepts like dielectric constant, for example, or Young's modulus become a bit ill-defined. So in some way, do we have to go to molecular simulations in some cases? And if yes, then when do you think it's important to interpret the AFM results?
Okay. Yes. For the three-dimensional AFM, the coupling of molecular dynamic simulations with the experiments, I would say, are essential to interpret properly the atomic details. They are essential. As I said, in this image here, we see features with atomic scale, but we could elaborate hypotheses, okay? But the confirmation of what the things are comes by matching simulations with experiments. So that is needed. What happened is that once you have refined your system and explain a given system with the theory and the simulations, then you can use that knowledge for the experiment to interpret by itself other systems, okay? Because you can just extrapolate, so yeah, the simulations are needed, but then after everything has been tuned, the experiments could walk along for a while.
Okay, very interesting. And the final question that I have is related to a comparison with the scanning tunneling microscopy. Of course, the principles are completely opposite, but to somebody from outside of the field of microscopy, it would look like, well, we get similar atoms on the surface. How would you compare the capabilities or sort of the outcome, the data-wise, what kind of conclusions you can draw from both cases, and especially when it comes to also the complexity of experiments in liquids, well, STM in liquids?
Well, the first thing is that there are some of the experiments that described today couldn't be performed with an STM in liquid because just the sample surface was an insulator.
Mm-hmm.
So mica, experiments on mica, for example, it couldn't be done with an STM.
So if we take a metal electrode, say a single crystal.
Yeah, you could you use with the metals. I think with a metallic surface, I guess the interpretation of the adsorbates on the surface, I guess it would be relatively similar. What the STM could never, I don't see how, but you could see the layering of the stacking of the solvent molecules on top of the surface. I think the AFM cannot get into that because in principle those layers are insulating materials, so the conductivity is not their conductivity. So yeah, I would say that regarding the surface, yeah, the information should be similar at the optimum for both techniques. Regarding above the surface, some features that appear here, like these layers, it couldn't be measured by the STM.
And what about the chemical sensitivity, meaning to a chemical element? Is there a big difference? Or there would be equally non-sensitive?
Well, in principle, I guess in the STM, at least in ultra-high vacuum, there is something called inelastic tunneling spectroscopy, where you could really detect changes in the tunneling current due to some inelastic interaction with some orbitals there, and that you could associate some kind of chemistry or signature. That in principle is not available for the AFM in this configuration.
Okay, thank you so much for this excellent and highly educational talk. So it's been a very long discussion, and I think we all gained a lot, and this talk will stay on YouTube so people can dig into these discussions for hopefully for many, many years. So as our audience could see, these force microscopy techniques offer fairly unique opportunities for the field of electrochemistry. They're not applied that much at all, I would even say, in the field. And so what I can say is maybe we should just hope that more people will join the efforts, and hopefully the big discoveries will follow. So with this, we're finishing today's colloquium. And thank you again, Ricardo, for your time and your efforts. It's been an amazing talk.
My pleasure, Andrew. Thank you for the invitation and for the attention of all the participants.
Absolutely.